Welcome back to our deep dive into large language models. In our last video, we explored the limitation of RNNs, the sequential nature, memory constraint, and the inability to handle long range dependencies. Today, we are diving into the solution that revolutionized natural language processing, the attention mechanism. This breakthrough from Google Brain research completely changed how we approach language understanding. Let's explore how. Before we dive into attention, let's quickly remind ourselves why we needed something new. One, RNN processed words sequentially, making them slow. They struggled with long range dependencies. They couldn't be parallelized effectively. They had trouble with context and ambiguity. So, a bunch of folks at Google Brain in 2017, they came up with one concept that is not just true to LLM but also true to life, I would say. To pay attention. If we do not pay attention, we lose context of the bigger picture. All right, so what is actually attention? Attention is the technique that created what they call transformers. Transformers is a whole different new type of neural network that use as their underlying kind of calculation the traditional neural network. And attention goes on top of that, creating some sort of a relationship in uh, type of these networks. Attention revolutionized NLP by solving two major challenges. Context, instead of relying on the immediate sequence of word, attention builds a complete picture of relationship across an entire sentence or document. Scalability, unlike RNN, attention processes all the words simultaneously, enabling parallelization. These makes attention ideas for handling today's massive data sets. Models can now process billions of parameters effectively, allowing them to grasp complex language patterns in an incredible speed. The key insight behind attention is beautifully simple yet powerful. Instead of trying to compress all the information in fixed size hidden states, why not let each word directly interact with the other word in the sentence? Let's start with the concept of attention. Traditionally, RNN focused on the sequential processing, where each word depends on the word before it, while using this approach struggled with context, especially for long sentences. Attention changed the game by linking all words in the sentence to each other. For example, the sentence, the teacher taught the student with the book, attention examines the relationship between teacher, taught, student, and book and teacher. And this doesn't stop there. Each connection is assigned a weight, which reflects the strength of the relationship. For instance, book might have a stronger connection to student and taught than to teacher. The web of relationship between the model understands the context historically, not just word by word. Let's take our example sentence. The teacher taught the student with the book. Watch what happens when we apply attention. Each word connects to every other word. Each connection has a weight or strength. These weights are learned during the training. Stronger weights indicate stronger relationships. Attention wasn't just a standalone idea, it became the foundation for transformers. Transformers use an encoder decoder architecture similar to RNN with one critical difference: self attention. Here's how it works. The encoder compresses input data like the sentence the teacher taught the student into dense representation, then captures the meaning and context. The decoder expands this representation into output, like translating the sentence into another language. Self attention ensures that each word in the input is related to the other word, providing a much deeper understanding of context than RNN ever could. Now, let's peek under the hood of transformers. Each encoder and decoder layer contains multiple attention mechanisms. These mechanisms analyze relationship between all input words, assigning weights to capture their importance. For example, let's say the model sees the partial sentence, the teacher taught the student with a. Thanks to attention, it knows that the most likely next word is book because it has already learned the relationship between student, taught, and book. This process repeats across multiple layers, creating deeper and more nuanced understanding at every step. Let's break down how attention actually works. Each word gets three representation: query, what it's looking for; key, what it can be matched with, and value the information it carries. The attention weight between the two words is calculated by comparing the query of one word with the key of the other, running this through a softmax function to get probabilities, using these weights to combine the values. Now, let's see how attention fits into the bigger picture, the transformer architecture. Multiple layers of self attention, feed forward neural network, residual connection, and layer normalization. The encoder decoder structure remains, but now the encoder processes input sequence in parallel, decoder generates output using both self attention and decoder attention, no more sequential processing. However, one thing we need to look at is transformer processes numbers, not words. This is where tokenizers come in. Tokenizers break down text into smaller units, words, character, or subwords, and assigns each unit a numeric ID. There are three main types of tokenizers. Word based assigns a single ID to each word. While simple, it creates huge vocabularies and struggles with synonyms. Character based assigns ID to individual characters. This reduces vocabulary size but carries less contextual meaning. Subword based breaks rare words into meaningful units while keeping common words intact. For example, faster might split into fast and allowing the model to reuse the part everywhere. There are three popular subword tokenization methods. Byte pair encoding. It is just an iterative approach that starts breaking the words from pre tokenization until we find an optimal vocabulary based on the frequency of pairs. Sentence piece. The main difference is that the byte pair encoding assumes that spaces are the ones separating the words. Here we are treating inputs as a raw input stream and we apply techniques on top of that. Okay, so there is no such assumptions in the word. This is a very good approach for languages where the hypothesis that spacing separates words are meaningless. Now let's look at three different models and what are the concepts they use. BERT use bidirectional attention, GPT uses autoregressive attention, and BART uses encoder decoder attention. Today, we explored how attention solved RNN's challenge, the inner workings of transformers, and the role of tokenization. In the next video, we'll dive deeper into transformer architecture, focusing on attention heads and how they refine contextual understanding. See you there.